So at this point, we've discussed the induced potential difference pretty well. Faraday's effect talks about current, though. We know potential and current are related, so let's see what that relationship is. First thing we're going to do is we're going to take our bar and we're going to place it on conducting rails. So that means we have a conductor moving on a conductor. This is an electrically connected circuit. So we'll be able to apply some circuit analysis here. Let's take our metal bar and let's pull it to the right with some force that we'll label F pull. So we're applying that external force. As we pull it, we're going to pull it so that it moves with constant velocity. That's going to be our observation, that it moves with constant velocity. This should already be telling you something about the forces. So we're pulling a bar to the right. It sits in a magnetic field that points into the page. The velocity is to the right. We know there's going to be an induced potential difference across the bar, and we know that that induced potential difference is going to be B times L times V. That's the process we reviewed on previous slides. So this induced potential difference, this came from a little positive charge moving upwards. So a little positive charge here, as the bar was pulled to the right, it felt a magnetic force that pulled it upwards. Okay, a positive charge moving up, that's a current. So charges move. That means there is current flow. So since we have a current flow, let's apply Ohm's law. Ohm's law says that the potential difference is equal to current times resistance. So we can solve that for our current because we're interested in what the current is. The potential difference across the bar, we've labeled that epsilon for induced EMF. That's divided by R to get our current. Let's fill in that that induced potential is magnetic field times the length of the bar L. Why don't we get that labeled in our picture as well? Times the speed with which it's moving divided by the resistance. Okay, so in our list here, epsilon is the induced potential. R is the resistance of the loop. So the resistance to the current flow. So if we have an induced potential and those charges are, the current is flowing because we're moving the bar, that means I is an induced current. The only reason we have a current in that loop is because we pulled the bar to the right. Okay, so that talks about the current. Now, I hinted at this a moment ago. I said we're pulling it and it's moving with constant velocity. Let's next ask what's going on with the forces. This page is a little bit full, so I'm going to spill over onto the next slide. So let's just pause and take stock of what we have. We have a bar that moves to a right. It has current that's flowing up, and that's a current carrying bar, which is like a current carrying wire. That's in a magnetic field. That's going to feel a magnetic force. So remember, magnetic force is equal to current times L crossed with the external magnetic field. So I is the induced current. And B is the existing field. So this is a magnetic force induced on the conductor or the moving bar. Whoops, there I tried to speak and write at the same time. That never turns out well for me. So magnetic force induced on the conductor, that sliding bar, moving in the magnetic field. If we want to get the direction of that induced magnetic force, We put our thumb in the direction of L, or the direction of current. Our index finger is in the direction of B, so that's into the page. See that the magnetic force points directly to the left. So this induced magnetic force, this opposes the motion. So that's really cool. We pull the bar to the right. Because we pull the bar to the right, it makes a current flow, which makes an induced potential difference. With flowing current, we get a magnetic force. That magnetic force makes the bar slow down. If you're thinking this sounds just like magnetic braking, you would be absolutely correct. And I'm going to show you an example of magnetic braking on the next slide. But first I want to pause and ask one more question about a result of that current in the bar. We know that current carrying wires have magnetic fields. So if there's a current flowing in that bar, it's going to create or induce a magnetic field. And that magnetic field, as long as our bar is close enough to the shape of a wire, is mu naught I over 2 pi r. If you do your right-hand rule, you'll know that your magnetic field makes circles around that bar, that wire, and the direction to the left of the bar, or inside the middle part of the circuit, is going to be out of the page. Okay, what's neat about that is that opposes the original field. So all this magnetic field stuff is actually kind of cool and interesting and neat. I think this is awesome. So all you have to do is slide that bar along. All of a sudden you get current, you get braking, and you get new magnetic fields. This is a demo of magnetic braking. So what I have here are two bars hinged on a rod. If I just perturb them to the side a little bit and let them go, you see that they swing back and forth pretty freely. They should have exactly the same periods. There's a tiny bit of friction at the top that's different between them, so it's not exactly the same period. But they both swing pretty freely. Okay, now what I'm going to do is I'm going to take this magnet. This is a very large magnet. It's really strong. It's also really heavy. And I'm just going to place it so that this rod is hanging between the magnets. So this is a really strong magnet. I'm going to pull them to the side, and now let's see what happens. So that guy stopped almost right away. Let's just look at that again. So it stops. So this is an example of magnetic braking. As the bar moves through the magnetic field, it induces a current in the field. That current feels a magnetic force. That magnetic force opposes the motion and brings the bar to a stop. Okay, so magnetic braking is actually a really good application. Many brakes, I'm thinking about, for example, the brakes on my bike, they just act through friction, right? You squeeze the brake handles on my bike and it slides a clamp along the wheel, and that's what makes it stop. Now, that's kind of damaging, right? It wears down the brakes and it wears down the bike wheel. Magnetic braking doesn't wear down anything, so this is a real super way to get objects to come to a stop. Let's go back now to having our conducting bar sliding without friction on conducting rails. We're pulling it so that it moves at constant speed v. And now let's ask about another thing that often we want to think about when we talk about circuits, which is power. So in this situation, how much power is dissipated? Well, I'm going to just quickly summarize some of the things we said previously. We're pulling it to the right. It moves with a constant velocity. That induces a potential across the ends of the bar and makes current flow up. That induces a magnetic force to the left, FB. We know that the induced current is the potential divided by the resistance. That's from Ohm's law. And we know that that induced potential is B times L times V. That gives us the expression for the current. That's an induced current. It only happens because we move the bar. We know that the magnetic force on the bar is also induced. It's equal to I times L times B. And if we put in that our I is BLV over R, we get that the induced magnetic force is equal to B squared times L squared times V divided by the resistance. And the direction of that force is to the left. More generally speaking, you could say that it opposes the motion. So the power dissipated by that force is equal to the change in energy over the change in time, or the work done by the force over time. The work done would be F dot delta x, that's divided by the time. Delta x over delta t, that's just the velocity. The velocity is to the right, the force is to the left, so that's F times V times cosine 180 degrees equals minus FV. Now I ran out of room a tiny bit, so I'm just going to spill down here. So that tells us that the force is minus, or the power, sorry, the power is minus force times velocity. Force we had above, so we'll plug that in. So our power then is minus B squared times L squared times V squared over the resistance R, where the negative sign shows that energy is dissipated. So we can calculate the power of these circuits as well. Let's continue with power by doing an example with some numbers. We have a 10 centimeter long wire. So there's our wire. It's pulled along a U-shaped conducting rail. So let's just draw the rail where they are in contact. In a perpendicular magnetic field, this time I'm going to make B point out of the page, just for something a tiny bit different. It's being pulled, let's say it's being pulled to the right. And it's being pulled with a constant velocity, 4 meters per second. The total resistance is 0.20 ohms. The length is 10 centimeters, 0.10 meters. And it says we cause 4 watts of power to be dissipated. Power is minus 4 watts. We include the negative because the energy is dissipated in the circuit. We're asked how big is the pulling force? So let's talk about what's going on here. Each little charge here, as we pull it to the right, it feels a force that makes that charge drift downwards. The velocity is to the right, the magnetic field is out of the page. That gives us a force that points down. If that little charge is pulled down, that means that the current flows in this direction. So current flowing down in the bar means that we're going to get an induced magnetic field to the left. So the induced magnetic force to the left. Notice here we're not asked for the magnetic force, we're asked for the pulling force. That's actually kind of significant. So let's start to pull all of these things together. I'm really quickly just going to be recapping things we've done in previous slides. The induced potential is B times L times V. The induced current is the potential over the resistance, equals BLV over R. The induced force on that rod, on that wire, is I times L times B, and this is the induced magnetic force. I'll put a B on it for magnetic. That turns out to be B squared L squared V over R. Okay, so we know the power, we know something about the force, we're trying to find the force, and we know the speed. Let's bring power into this. Power is equal to force dotted with velocity. That's the magnetic force. Because they're in opposite directions, F dot V is F times V times cosine theta, where theta is 180 degrees. So that equals minus FB times V. So FB is minus power over V. So that's equal to minus 4 watts divided by 4 meters per second. This gives me the magnitude of the magnetic force is 1.0 newtons. Now, we weren't asked for the magnitude of the magnetic force. We were asked for the pulling force. So in the horizontal direction, the sum of the forces on that bar is mass times acceleration. It's constant speed, so the acceleration is 0. So F pull minus FB equals 0. The pulling force and the magnetic force have to have the same magnitude. Okay, so that's a small step and it's a little bit subtle, but it's important not to skip over it because we were only able to solve for the magnetic force. We then had to apply Newton's second law to find the pulling force. If our bar was accelerating, it would be a different story. Okay, so part B, what is the strength of the magnetic field? We know the force, so we can use our force equation now to solve for B. So FB equals B squared L squared V over R. So B squared is equal to R times FB over L squared V. Take the square root to get our B. B is the square root of R FB over L squared V. We'll put in R equals 0.2, FB is 1 Newton, L is 0.1 meters. V is 4 meters per second, and what we should get for our B is 2.24 Teslas. The question asks for the strength of the field, so we don't have to give our answer as a vector.